Now we were in the midst of an example last time, and the example was a function on R to R defined by f of x equal to x if x is irrational, and 1 minus x if x is rational. Now what we have shown is that this is continuous at 1/2. Okay, we have already shown this, right? Okay. Now here, now this is y equals x, 1, 1. This is y equals 1 minus x, and this was 1/2. Now, if x is in Q, then this was the point on the graph of the function, and when x is in R minus Q, this will be the point on the graph of f. So long as x is different than 1/2, say this, there will be a distance between the 2 points. So, well, if x is in R minus Q, the functional value will be equal to this. If x is in Q, then the functional value will be this. Now, we'll use the fact that no matter what non-empty interval in R you take, it contains both rational and irrational numbers. Thus, if the point itself, if that's rational, then we'll take any neighborhood of that point that will contain irrationals and vice versa. But it might be useful to go through the proof, considering also the technical details. But in the proof of this, part of triangle inequality, an extended triangle inequality, that will be useful, and that was one exercise in the first exercise set, but let's go through that. Now, let xy be in V, where V is a normed space. With norm with some norm. Now, if you take the individual norms of x and y and take the absolute value of that, that will be less than or equal to both x minus y, the norm of that, and less than or equal to the norm of this. Have you gone through the proof of this in the exercises? Or shall we do it quickly? Now let's do it quickly. We have, now we wish to relate the individual norms of x and y with the norm of either x minus y or x plus y. So let's start with the norm of x. But we can write this as x minus y plus y. And using the triangle inequality, this will imply that the norm of x minus y plus the norm of y. So the norm of x minus the norm of y, that will be less than or equal to x minus y. But now we can interchange here the rows of x and y. We similarly get, that is, we start here with the norm of y, that's norm of y plus x minus x, and we'll have that y minus x, the norm of that, is less than or equal to the norm of y minus x, but that's the norm of x minus y. So this number and its negative, they are both less than or equal to this quantity. So the absolute value of x minus y, that will be less than or equal to the norm of x minus y. How can we get this x plus y, the norm of x plus y version? Well, simply replace y by minus y. The norm of minus y and the norm of y, they are the same. Moreover, let me write it in full. This is equal to the norm of x minus the norm of minus y. But by what we have shown, that's equal to the norm of x minus y, which is x plus y. Okay? So we'll use this in showing that pictorially that this will be discontinuous at each x different than 1/2. That's clear. But the point is, this distance that heavily depends upon what x naught we take. If we take x naught close to 1/2, that distance will be small. Far away from 1/2, that distance will be large. So the epsilon delta that we use, that has to be dependent upon. Well, given any epsilon, there is some delta such that the required condition holds for continuity. Well, if it's continuous at some point, well, delta will depend upon not only epsilon, but also the point we take. If we show the negation of that, in case f is discontinuous, this time we should show the existence of some epsilon, such that no delta will work. Well, the choice of that epsilon in that case will depend upon what point we consider. Okay. Well, take any x naught in R different than 1/2. Well, what's this distance at x naught? Well, it's depending upon whether x naught is in Q or not. Well, it will be 2x naught minus 1 or 1 minus 2x naught. It will be x minus 1 minus x or 1 minus x minus x at x naught. But we can take the absolute value of that. Now, the absolute value of 2x naught minus 1, that will be positive. Let's make epsilon dependent upon this. Well, let's take 1/2 of this. The claim now is that no matter what x0 is, so long as it's different than 1/2, and no matter what delta we take, the condition of continuity at x0 will not be satisfied. That's what we'll show, okay? But, okay, take any delta positive. But we need to distinguish between the two cases where x0 is irrational and when it is rational. So let's do that. Case 1. Assume that x0 is in R minus Q. Now we'll consider the delta ball about x0. But what's important here is that that ball will contain rational points as well. Now, the delta ball about x0 intersected with Q, that will be non-empty. Pick some member from here. So this will be a rational number, and it will be delta close to x0. But we can choose it actually as close as we wish, so long as it's less than delta. So with let's choose it such that this is less than epsilon as well. We can do that. Just take the minimum of epsilon and delta, take that ball, that the intersection of that with Q is non-empty again. Okay, now let's check what happens to this. Then f of x minus f of x0. Well, here we're in R, the usual distance. The distance between f of x and f of x0 is given by this. Now let's write out in detail what this means. X is in Q, f of x is 1 minus x. x0 is, in this case, irrational. So we'll have minus x0. Okay? But now we wish to show that this is, if the choice that turns out to be an appropriate one, what should we be showing in order to reach a contradiction with continuity? This should be larger than or equal to epsilon. Epsilon is given. We take any delta. If we find some point in the delta ball about x0, x, such that f of x and f of x0 have a distance according to the usual metric larger than or equal to epsilon, that'll complete the proof for this part. Oh, but epsilon is 1/2 this, so let me rewrite this as 1 plus x naught minus x minus 2x naught. So I have added and subtracted 1x naught, but now this is 1 minus 2x naught minus x minus x naught. Well, this is a norm. Now I can use this inequality. This will now be larger than or equal to the absolute value, which is the norm here, of 1 minus 2x naught minus x naught, the absolute value of this. What do we know about this quantity in terms of epsilon? This is just 2 epsilon. What do we know about this? This is less than epsilon. But then this is larger than epsilon. Well, we'll do the dual of this in case x is equal to x naught is in Q. But let's do that as well. Case 2. This time x naught is in Q. Well, this time let me write it like this. Let it's the same thing, but let epsilon prime be the minimum of delta and epsilon. That will be positive. Now, by property of real numbers, which we borrowed from real analysis, B, let me write this delta prime. B delta prime, x naught, intersection, this time R minus Q, is non-empty. Pick some x in this intersection this time. Now here I have chosen delta prime such that this is automatically satisfied. But then, again, let's consider f of x minus f of x naught. Here, since x is in R minus Q, f of x is x. And since x naught is in Q, this time this is 1 minus x naught. This time, let me add and subtract x naught. But now I have from here x naught plus x naught, 2x naught minus 1. And what remains is x minus x naught. Or minus x naught minus x, since we have written this in terms of x minus y. But now this is larger than or equal to, by the inequality shown here, the absolute value of 2x naught minus 1 minus the absolute value of x naught minus x. What do we know about this? That's 2 epsilon. What do we know about this? This is less than delta prime, but that's less than or equal to epsilon. So this is larger than epsilon again, completing the proof that f is not continuous at any point in R other than 1/2. So f is not continuous at any x0 in R with x0 different than 1/2. Now, in fact, the question that I posed preceding this example was, given a non-empty finite set in R, can you construct a function which is continuous at exactly the members of that finite set, but discontinuous everywhere? But now, since finitely many members of R will be discrete, they will be away from each other, well, at each point, you can actually make a construction of this type and then combine the functions in a way that they turn out to be just continuous at the given points and discontinuous everywhere else. I leave that construction as an exercise to you. Okay? Any questions about this? Okay. Here, what we have done is we have actually translated this picture into a formal writing. But the gist, the crucial point was this choice of epsilon, that should be dependent upon x0 because it should be made dependent upon this distance. Okay? Okay. Now, what we have done so far concerning continuity is, well, we have defined continuity, and then we considered local properties, that is, continuity at a given point in the context of metric spaces. Now, we'll have another simplifying theorem, well, in the context of general topological spaces, but this will refer to global properties of continuous functions. That is, we will find some equivalence to a function being continuous on its entire domain, rather than locally just at the point. So, this is about global properties of continuous functions in topological spaces. Now, well, then we need two topological spaces first. Let x tau and y tau prime be two topological spaces, and we need a function f on x to y, a function. Now the following are equivalent. One, here, one will consist of saying that f is continuous, is globally continuous, that is continuous on x. F is continuous on x. What's 2? What's that equivalent to? It will turn out this is equivalent to, for any open set G in Y with respect to tau prime, of course, in Y the topology is, one has that F inverse G. Let me remind you of the definition of this. This is just those points x in x such that f of x is in G. That is, here we have x, here we have y, this is f, here we take some G, any subset of this, then F inverse G, this is the collection of all points which are mapped under Y to some point in G. This is open in X with respect to tau. So if openness is preserved under the inverse of the function f, which is not a function itself unless f is a one-to-one and onto, but it's a set-valued map, well, openness gets preserved. If you go from y back to x under f inverse, that's equivalent to continuity. But what we expect is, if that's the case, then we should have some similar characterization of continuity in terms of closed sets. Well, and it turns out for any closed set C in Y with respect to tau prime, one has that F inverse of C is closed in X with respect to tau. Now let's prove this. One implies two. Well, let us then start. Assume that f is continuous on X. Now, to show the two holds, we need to start with an arbitrary open set G in Y. Let's do that. Let G be any open subset of Y. Well, that this is with respect to tau prime, and that in X we have tau. Since that's clear, I will suppress with respect to what topology. Now we need to show that F inverse G, that's open with respect to tau. Now we can do that in several ways, but there are two useful characterizations for that. Well, if I take any point in F inverse G, and F inverse G turns out to be neighborhood of that, if a set is a neighborhood of each of its points, then that will be open. Or if any X is an interior point, that's the same. We have no balls here, no metric, no epsilon balls. Okay? Now assume that X is in F inverse G. Of course, F inverse G might be empty as well. G need not be empty. Well, the function might be such that you take G here, but everything in X is mapped onto somewhere not in G, outside G. This might be outside the range of the function. But this also includes that. I did not say let X be in F inverse G. If I say let X in F inverse G, then it's my duty to make sure that F inverse G is non-empty. Well, then I would have to consider two different cases. Assume that G is empty, then F inverse G is empty. Well, otherwise F inverse G is non-empty, and so on. But if I say assume that X is in F inverse G, well, if F inverse G is empty, that assumption will false. Well, in that case, whatever follows, P implies Q. If P is false, then that will be true. Okay. Well, then F of X, that will be in G by definition of F inverse G. But this is an open set, and this is a point in there. And what we can use is continuity. Well, to observe what relationship between F of X and G will be useful if we wish to use continuity somehow. Well, F is continuous at X. What does that mean? For every neighborhood V of F of X, there is some neighborhood U of X such that F of U is contained in that neighborhood. Is this a neighborhood of F of X? Yes. Any open set containing a point is a neighborhood of that. Now, G is a neighborhood of F of X. But as F is continuous at X, because it's continuous everywhere, there is some neighborhood U of X with F of U being contained in G. Okay. But now, if I take F inverse of this set and F inverse of this set, the inclusion will be preserved. Then F inverse F of U will be contained in F inverse G. What can we tell about this set? It need not be equal to U, because here, let me make another picture. If this is U, this will be F of U, some set in here. But if I consider all points in cap X such that their image falls into F of U, surely any point in U will be sent to some point, onto some point in F of U, but there might be other points as well which are sent to here. So what we know is that U is contained in here. But that's also what we need. What was U? It was a neighborhood of X. What can we tell about any superset of a neighborhood of a point? That will be neighborhood as well. Since U is a neighborhood of X, so also is F inverse of G. Does that complete the proof? Well, we have taken some arbitrary point in here and have shown that F inverse G is a neighborhood of that point. So what we have shown is that F inverse G is a neighborhood of each of its points. Thus, F inverse G is a neighborhood of each of its points. Hence, F inverse G is open. Completing the proof of this implication. Now let's also consider 2 implies 3, 3 implies 1. That will be left to you as an exercise. So let us start by assuming that 2 holds. In order to show that 3 holds as well, let us take any closed set C in Y. Let C be any closed subset of Y. But the only thing we know is that open sets are preserved under the inverse of F. Well, let's use that, but in order to use that, we need some open set in the range, which will in this case naturally be Y minus C. Then Y minus C is open by 2 F inverse of Y minus C is open. We're interested in F inverse of C. But how are F inverse of C and F inverse of Y minus C, how are they related? Let me draw once more a picture. Now this is C, this is Y minus C. Everything in here is sent onto some point in Y. But F inverse of C, well, these are the totality of all points which are mapped on C. Thus, nothing from here can be mapped onto here. So F inverse of C and F inverse of Y minus C, they are disjoint because by definition of a function, it will be sent to exactly one point which cannot belong simultaneously to C and Y minus C. But everything will be sent to something, so this is a partition of cap X, which means that X minus F inverse of Y minus C is nothing but F inverse of C is closed, since F inverse Y minus C is open. Just by definition of closeness. The complement here, that's open here. Well, so 3 holds. that's left as an exercise. Okay. Now, let's come back to our agenda. Why did we deal with compactness? Well, we wanted maximization and minimization problems to possess solutions. So we wanted to extend finiteness in an appropriate manner. But that by itself, in isolation, did not work. We needed to impose some smoothness conditions on the function in question. So the function should be well behaved, and we have introduced continuity. So thus what we expect is that if we have a real valued function, which is continuous on a compact set in its domain, should attain both its maximum and its minimum on that set. Now we will very soon arrive at that result, but for that we need one more important aspect of the conjunction of compactness and continuity. That will be a theorem which bears the title Preservation of Compactness under Continuous Functions. If K is a compact subset of the domain, then its image under a continuous function f in the range, that will be compact as well. So here again we need two topological spaces. Let x tau, y tau prime be topological spaces. K, a non-empty subset of X, and f on K into Y, a function. Here, for f of K to be a compact subset of Y, I don't need continuity of f on the entire cap X. If it's continuous on cap K, that suffices. And here our convention is K is considered with the restriction we relativize the topology tau on cap X to K, and that's considered with that relative topology, under that relative topology. Now, if K is compact and f is continuous on K, then f of K is compact. Of course, this compactness with respect to tau and this compactness with respect to tau prime. Well, this will have a relatively simple proof. Assume that. First, let's start K is compact and K is compact, and f is continuous on K. Here, how to proceed is, in view of the preceding theorem, pretty intuitive. we wish to show that f of cap k is compact if we start with an open covering of that set, then the inverse images of the open set in that collection, they will be open in the domain in cap k, and we expect them to cover cap k, in which case that will lead to the existence of a finite subcovering of that for cap k, but then we can possibly produce a finite subcovering of the original open covering of f of cap k for f of cap k, and that will work very smoothly. Assume that script g alpha in I, where I is a non-empty index set, that's our convention, I will not write that, is an open covering of f of k. By the above theorem, f inverse g alpha is open with respect to tau for each alpha. So if the union of these contains cap k, then the collection of f inverse g alphas, that will be an open covering of cap k. Now take any x in cap k. Well, will it belong to one of these f inverse g alphas? But then f of x, that will belong to f of cap k. But the g alphas form an open covering of f of k, so f of x will belong to g alpha for some alpha. That is, x will belong to f inverse g alpha for some alpha in I. Thus, the collection f inverse g alpha such that alpha is in I is an open covering of k. Well, let's give a break at this point and continue with the agenda next hour. But if this is an open covering of k, since k is compact, this has a finite subcovering for k. Now, since k is compact by hypothesis, there is some finite non-empty subset E of I of the index set such that f inverse g alpha, alpha in E, is a finite subcovering of f inverse g alpha, alpha in I for k. That means the union of this that contains cap k. Now what we expect is we now claim that if we take the corresponding finite subcollection of G, that will be a finite subcovering of script G for f of k. G alpha, alpha in E, is a finite subcovering of script G for f of k. The only thing we need to show is that f of cap k is contained in the union of G alphas when alpha ranges over E. Okay? So assume that Y is in f of k. But this is the collection of the images of members in cap k. Well, in that case, Y is equal to f of x for some x in cap k. Then Y is equal to f of x for some x in cap k. But what do we know about this x in cap k? Since this collection is a finite subcovering for k, then that x must belong to f inverse G alpha for some alpha in E. But then x is in f inverse G alpha for some alpha in E. But if that's the case, then f of x is in G alpha. X being in f inverse G alpha by definition means that f of x is in G alpha, implying that f of x is in G alpha. So any point in cap f of k turns out to be in the union of G alphas when alpha is in E. But that simply means, thus, G has a finite subcovering for f of k. But that's nothing but the definition of compactness of f of k. Hence, f of k is compact. Now that takes us to our first optimization theorem. The proof of the optimization theorem, that will be short, because we have made everything ready for the proof. Theorem let x tau be a topological space. Here, the second topological space, that will be R under its usual metric, because we will consider optimization of real-valued functions, the existence of maxima and minima of real-valued functions. And K compact. Let F on K to R be a function. Well, it will be the same, but let me write it like this. Because I want to have compactness of K and continuity of F in the same place in the statement of the theorem. Formally it makes no difference at all. Now, if K is compact, of course, with respect to rho, and F is continuous on K, then there are points x upper star and x lower star in K such that f of x upper star is equal to the maximum of f of K and f lower star x is equal to the minimum of f of K. This was what we were aiming at, right? Putting appropriate conditions on K, an extension of finiteness, and putting some well-behavedness, smoothness conditions on F, that's continuity. So here, compact and continuous. Now let's prove this together. So we'll start, assume that K is compact, and F is continuous on K. Now you will discover every statement which will follow. F of cap K, that's a subset of reals, and the claim is that that subset of reals has both a maximum and a minimum. What do we know about F of K as a subset of R? Just by the preceding theorem. F of K is compact. Well, if a set of reals possesses a maximum and a minimum, then it has to be bounded. Is F of K bounded? Where do we know that? From Heine-Borel theorem. F of K is a compact subset of R, which is a Euclidean space. Then F of K is both closed and bounded. Then F of K is closed and bounded by Heine-Borel theorem. Well, we know the maximum of F of K is the supremum of F of K, and the supremum should belong to the set for it to be the maximum. Well, does F of K possess a supremum? Well, if it's bounded, that means it has an upper bound and a lower bound as well. But let me also note the following. Now, f of k is a non-empty subset of R, as k is non-empty. And f of k has both an upper bound and a lower bound, since it is bounded with respect to the usual metric. But a non-empty subset of R, which has an upper bound, what happens to that set? It has a supremum. And a non-empty subset of R, which has a lower bound, has an infimum by the supremum and infimum principles, respectively. Now, let me give names to those. M supremum of f of k and lowercase m infimum of f of k both exist by the supremum and infimum principles, respectively. What's left? To show that cap m is a member of f of cap k and lowercase m is a member of f of k as well. But now let's go back to our very first proposition. When is an upper bound of a non-empty subset of reals equal to the supremum of that? If every epsilon ball about it has a non-empty intersection with the set. Okay. Now, from our first proposition, well, not first, from one of our first propositions, for any epsilon positive, the epsilon ball about m intersection f of k is non-empty, and the epsilon ball about lowercase m intersection f of k is non-empty. Now we had an upper bound, then we took y minus epsilon, the interval from y minus epsilon to y, that should have a non-empty intersection with the set whose upper bound y is, but then we brought that to a common formulation for upper and lower bounds. That was this. But what does this mean about cap m in its relation to f of k? It's a limit point. Well, a point is a limit point of a set if and only if each of its neighborhoods has a non-empty intersection with the set. But we have seen in the context of metric spaces, well, epsilon balls replacing neighborhoods, that works as well. Thus, m and lowercase m are limit points of f of k. Do they have to belong to f of k in that case? F of k is closed. It contains all its limit points. As f of k is closed, m and m, they both belong to f of k. Thus, there exists x upper star, x lower star in k with f of x upper star equal to the supremum, but that's the supremum which belongs to the set, is the maximum. Maximum of f of k and f of x lower star is equal to the minimum of f of k. Here we used preservation of compactness under continuity. Then we used Heine-Borel theorem. Then we used the supremum and infimum principles. Then we used that the supremum, an upper bound is the supremum if and only if it's a limit point. Likewise for the others. Using closeness, we concluded that these belong to the set itself.